we're happy to be hosting here Dr. Richard Gorman. He's a research scientist at NOAA, which is the National Institute for Water and Atmosphere in New Zealand. That's corresponding, a little bit corresponding to NCEP in New Zealand. They run operational models for weather forecasting, and Richard has been working with wave modeling for the last 30 years. That being nice, perhaps 40?
No, I can't exaggerate.
And once again, I'd like to ask everybody to meet us. And today, Richard, he introduced to us on the sidelines to his visiting his sabbatical here, a new workflow that was developed by a colleague at NOAA called Dr. Hilary, and the workflow manager is called Cylc. And by serendipity, I found out that Cylc is being considered one of the components of our future unified workflow manager, NCEP. So when Barry McGinnis, who's also online and part of the Crow development team, you heard about that. He thought it would be a really good idea if we could actually have a presentation about Cylc, which is of interest to everybody. I particularly have been using Cylc in my work for about a month and a half now with one of Richard's developments, which is non-linear optimization tool for numerical weather prediction models. And it works great. It's a fantastic product. I think it's going to be really beneficial to everybody, not only within the Crow framework, but at the individual level. If you need a workflow manager, this is really a go-to tool. And I hope everybody finds some benefits of the presentation today. I'm sure most of you will. Before passing on to Hilary, who's online, I'd like to ask Richard if he would like to make any remarks.
I think found Cylc a really great framework for running all sorts of workflows, particularly in our operational system. And as you can see, I've been able to adapt it to all sorts of other things like our optimization suite. So, you might as well hand over to Hilary.
Excellent. Okay, so take it away, Hilary. Thanks for joining us today and for making the time to, share with us your great product.
Well, thank you for having me. And thanks for the introduction. So I actually did my PhD in the US in the 1990s. And when I first arrived there, people had trouble understanding my accent, so I tried to modify the way I spoke. But then I came back to New Zealand in about 2000, so I've probably been regressing ever since, so I hope you can understand. I guess Richard's probably been swapping you up with a Southern Hemisphere accent. So, okay, I'm on a Windows laptop here, and I have my presentation and demonstration on a Linux VM. So I will just maximize that. Can everyone see that okay?
Yeah, that's good.
All right, we'll go with that. Right, so, by the way, how much time do I have? I think I forgot to ask that, so we may have to wing it a little.
I give her 1 hour, and we have a 30-minute discussion. Time is reserved.
All right. We'll see how we go. Quick outline. I'll go over a little bit of the history of Cylc, why it was developed, and who's using it, and a little on cyclical workflows, or cyclical workflows, what are they, and how Cylc manages them differently to other systems. A little bit about the architecture of Cylc itself and how you define workflows in this. And then finally I'll attempt a few demonstrations, live demonstrations. So, a bit of history. NOAA, where Richard and I work, we started doing operational forecasting relatively recently, about 2007. Various environmental models driven by weather models. Pretty small compared to you guys, I think, but nevertheless, a proper operational system. And we ran into trouble because the workflow manager we were using could only do what I call fixed cycling, which means it always had to finish a whole forecast cycle before you could start the next cycle. And on our supercomputer at the time, which was getting old, that caused major problems whenever there was a delay or a problem, a failure. It often resulted in 24-hour catch-up before we were back in, caught up real-time operation again. The annoying thing about that was, in fact, the individual job dependencies between cycles did not require waiting for a whole cycle to finish before starting the next one. So we went to work trying to figure out how to make a workflow manager that was not constrained by that. And we came up with Cylc. That's leaving out a lot of hard work, of course, but the result was, on that particular system at the time, probably about 2010, I think, we first went operational with Cylc, early versions of it. We reduced that 24-hour catch-up to 30 minutes. That sounds very hard to believe, but it was actually true. Of course, it's very dependent on exactly what kind of system you're running and whether or not you have the compute resource to run a lot more tasks concurrently, which still can do in certain situations. So just to set the background for what a lot of my slides will look like, that's a little diagram of a workflow. Each blob represents a task, which is the workflow manager's abstraction of a job that runs on a computer somewhere, and so those are the nodes, and the edges, or the arrows, are dependence between the tasks. So in this case, the task foo can only run after the task prep has finished, and so on. So that's just a little one-off workflow. Now, to illustrate what I was saying about Cylc and our operational systems, here are two consecutive cycles of a similar small workflow with 6 tasks in each. And these star-shaped ones represent real-time clock-triggered tasks that might be waiting on real-time observation. So we run this whole blue workflow and all the jobs in it according to their dependencies, and then there'll be some time gap, and 6 hours later we do it all again. And these dotted arrows represent the actual dependence between tasks across cycles, which doesn't matter if you can wait before starting the next cycle, but if you want to lead cycles for more efficient scheduling, then it does matter. But you could imagine that task A, for instance, is an environmental model of some kind, and each forecast that it starts depends on a state file generated by the previous instance, so that explains that dependence. But there can be other kinds. On the right here is a job schedule representation of that system. So time goes toward the right, and each of these boxes represents a job and how long it runs, and the vertical stacking shows concurrency. So if you look at the start here, as soon as task A finishes, B and C can start at that point, and so on. And then the whole system finishes, and we wait for the new cycle and start again. So the problem is, if there's a delay, such that this cycle runs into that cycle, well, if you've got a fixed cycling system, the best you can do is cram those two together to reduce that gap. And this is what you get. If you imagine here, this delay of almost the whole cycle results in this forecast cycle intruding into the next cycle, and so on. And in this particular case, you can see that it does indeed take something like 24 hours to catch back up to real-time operation, which is the grey here. But with optimal interleaving between cycles, and across cycles rather, which is what Cylc can do, you can in this particular case, catch up within a single cycle. And that is what we managed to achieve on our original deployment of Cylc. So it's now an open source project with a website you can download the code from. And hopefully this animation shows up across the video link. I found that a tiling map that scrolls makes it look like there are even more places using Cylc, so I used that. That was as of about a year ago. And there's a list of institutes using it to some degree or other. The big site, of course, is the UK Met Office, which is enormous, and it's been using Cylc to a pretty much industrial level for 2 or 3 years now, and it's gone very well. So, what is a cyclical workflow? I'm sure you will all be very familiar with this, but there are several reasons why you might need a cyclical workflow. One is real-time forecasting. Oops, typo there, sorry. Run everything again whenever new real-time data comes in. There are other reasons too. Another is you might need to split a long model integration into many smaller chunks and have an associated workflow with each chunk. And that's the sort of thing you do in climate and earth system modeling. And however, you could also just simply be wanting to process a whole lot of similar data sets, a sequence of data sets, such as in satellite data. That should be data, sorry, processing. So, I'll illustrate cyclical workflows now. So here's a simple single cycle and a second cycle of the same thing. Something different often happens in the first cycle with some kind of preparation tasks. And we'll assume that there are these two dependencies that go across cycles. And the same again for the third cycle. Now, Cylc sees those dashed dependencies as on equal terms on equal terms with the intra-cycle dependence. So that really looks like that. It's just a single workflow that happens to be composed of cycling tasks which repeat. And if you take away the cycle point boxes, you can see there is indeed just a single monolithic workflow. However, it does go on and on forever. And that's the challenge to manage something like this. So, how can you manage this kind of system? Statically, you can actually manage workflows like this so long as they're small and finite with a workflow manager that does not understand cycling. You just have every single instance of a cycling job represented as a different task in your workflow manager. So I'll illustrate how this works now. So now we've got 5 cycles of that simple workflow. And on the right, I'm going to show how we can run this. Green represents a running task, blue is a waiting, so its dependencies have not been met, and grey will represent a finished, succeeded task. And you can see that we just trickle through to the end of the workflow, and even in this case, you actually have tasks from 3 different cycles running at once a lot of the time. But a fixed cycling system, which has to finish one cycle entirely before starting the next, as I said before, it's okay for real-time operation mostly when you do have a natural delay between cycles, but it's very inefficient in other situations. A little illustration of that. So we finish that cycle, then start the next one, and so on. There's only ever tasks from a single cycle running at the same time. Finally, the way Cylc does it it treats the workflow as a single ongoing workflow that happens to be composed of individually cycling tasks. There's no global cycle loop in Cylc at all. It's only individual tasks which advance to the next cycle. And they're constrained only by their own individual private dependencies. So this sort of produces a window on your workflow. And it performs as well as a static workflow manager that doesn't understand cycling on a single workflow. So let's illustrate that in a little video. So you can see that these tasks at the top end of the workflow, foo, are advancing as they see fit to the next cycle, regardless of what's happened earlier on in the previous cycle. I just paused that. It's going a little fast. I will let it finish. I should play that once more. I'll pause it. Right, pausing the video there. So you can see here that in the final task in the first cycle has yet to run, but the top level task foo in the second cycle is already running, and each task, regardless of where it is, which cycle point it belongs to, it runs as soon as its own individual dependencies are satisfied. And finally, I'll show you how the system adapts nicely, even if things go wrong during the workflow. So in this case, on the right-hand side, it is going to be a task, this one here, I think, Baz, going to fail in the third cycle and retry several times after a delay before it succeeds. And you'll see that the upstream tasks carry on. Oops. As if nothing has happened, because they don't depend on this. It doesn't matter to them. And this guy doesn't care either. It doesn't depend on the fail task. It only delays this one. And then once this one succeeds on its third try, everything else can catch up. And I'll just show how, in the end, in this case, we get to the end of the workflow just as quickly as if nothing had gone wrong, which is the case on the left. I'll start both of those at once. It's maybe a little hard to follow in real time, but it's just to give the impression. So here we are approaching the third cycle. This one's going to fail and turn orange, I believe. Sorry, I got ahead of myself there. This is the same one I showed before. This one. Apologies. Right, so we've got cycling as Cylc does it with no problems occurring, and on this side, in the third cycle, this task is going to fail several times. There it goes there, turn orange. So wireless's task below it cannot proceed, and neither can that one, but task foo, as I said, doesn't care, so it just keeps on going. And it's failed again, so we're really stretching out across multiple cycles now. And it's going to run 10 cycles to the end. Now, on the third try, it's succeeded. So everything downstream, because it happens to run faster than the upstream tasks, is going to catch up quickly. And in the end, in this case, they both reach the end of the workflow at the same time, of 10, for 10 cycles of the workflow. So that's the way Cylc manages cycling workflows, which I think is very different to any other system for cycling workflow managers. Now, so there's no connection at all to real time at this point. The way we handle that is you attach clock triggers to particular tasks if you need that. So if this task was to wait on real time observations, you would attach a clock trigger to this, and in addition to its dependence on other tasks, it would wait on a particular wall clock time before it could run. So, a little bit about the architecture of Cylc and a Cylc-based system of workflows. So Cylc has no central server at all. Typically, other workflow systems used in WebAssembly, for example, have a huge central server that runs all suites for all users, and that has, in my view, a lot of administrative overhead and a big security footprint, because the system has to run with special privileges on the system. But there's none of that in Cylc. Every suite is an island unto itself, and it gets an ad hoc daemon process that starts up to run it for the lifetime of the workflow. And for a given suite, a given workflow, it only requires the system with the command line and GUI interfaces. There are also no agent processes on job hosts, because you can run distributed suites with Cylc. You can run jobs on other systems via PBS, Slurm, and a bunch of other resource managers. Instead, we automatically wrap jobs in some boilerplate code that communicates progress back to the daemon. Everything runs as a user on the suite, on the daemon host and the job host. So it's very lightweight. I mean, as a researcher, you can simply download Cylc onto your own VM, unpack it, and start working with it. But for big cases like the Met Office and to a lesser extent NOAA, you can scale up by simply adding as many VMs as you need to run as many suites as you need. Here's my favorite picture ever of a supercomputer. Just a little illustration of where you might run, how you might run Cylc in an HPC environment. We typically run the suite daemons. This is meant to represent one suite. Whoops, one suite daemon here. I'm assuming you can see my mouse pointer, which is massive. And it may run jobs on other Linux boxes and also on your HPC. Now, you can actually run the daemons as well on your supercomputer if you want, but that's generally not thought to be a good idea. But you can do it. So, user interfaces, we've got a pretty powerful command line interface. For instance, this single command here will re-trigger manually all the tasks in the suite called Experiment 1, with cycle points starting with 2020, names starting with get underscore, and which are in the failed state, and it won't touch any other tasks. And we have a control GUI, graphical user interface, for individual suites, and another one called gscan, which can show multiple suites on multiple hosts if you are running more than one. Just a little note there to say that currently our GUIs are written in PyGTK, which is becoming somewhat obsolete. And we're aiming in the future to develop web GUIs. But we aren't there yet, unfortunately. We're somewhere there. Our suite daemons are now web servers. So that's what the graphical user interface looks like. Don't worry about all the information here, just to say that each task is represented by an icon with a color that represents its state, and this particular suite is deliberately designed to go through many different tasks at states. It doesn't normally look this colorful. So, and here's a list of the states here against each task, where the task is running, the host, the job system, and the job ID. In this case, it's just background jobs and process IDs, but it could be, say, PBS and a PBS job ID, time the job started, finished, and so on. You can also get if your suite's not too enormous, a live dependency graph view of your workflow that runs, and you can interact with individual tasks by clicking on them. And so that's the multi-suite summary G-scan interface. Time is moving on, so I think we'll just skip over that for now. This shows a particularly enormous suite. This is from the Met Office, the UK Met Office, just to show the kind of thing that is now possible to run with Cylc if you need to go there. That's a global forecasting ensemble suite from a couple of years ago. Apparently it's got even worse since then. A couple of zoom-in views of individual tasks in there. So we have very efficient ways of generating, if you're running ensembles, of generating large numbers of similar tasks without duplicating all of the associated configuration. That's just proving that you can now connect to Cylc Suite Demons with a web browser. However, that's clearly not a very usable web interface yet. Right, a little on basic workflow definition. How do you actually construct and run a workflow with Cylc? So it's a simple extended any text config file format. However, you can embed Ginger 2 code in it in order to programmatically generate any aspect of the suite definition if you need that. Ginger 2 is a template processor from the world of web development, and it essentially allows you to put Python-like code in amongst arbitrary text. It's arbitrary to Ginger 2, and it slices and dices the text file for you to generate the final suite definition that Cylc sees and processes. Anyway, because this is a simple text file format, you don't have to be an expert software developer to write simple suites. Large real suites typically do use a fair amount of Ginger 2, however. I have run into a number of people who think that graphical GUI-based workflow definition systems are a good thing, but I really strongly disagree with that. This text file format allows you to treat complex workflow definitions just like source code, and can be, for management of source code and collaborative development with proper tools for doing that. So here's a simple Hello World suite in Cylc. This is an actual workflow definition you can run. It has sections denoted by square brackets, and everything else is a config file is simply item key equals value items. This first section, scheduling, defines when tasks can run, and this shows dependencies between tasks, among other things. So here, the task goodbye triggers off of hello when it finishes. And then in the runtime section, you define what to run and where and how to run it, which isn't shown in this suite, when these tasks are ready to run. So what Cylc actually does here at runtime is it takes what you've defined for the task and wraps it in the job script, which can be submitted to run on the desired job host. So if you don't specify that, it will simply default to running your jobs as a background job on the same host that you're running the suite thing on. And also, what you actually run can be inline scripting, or it can be external scripts or executables, or any combination thereof, and can even be multi-line scripting. That's what I'm saying here. Here's a slightly more complicated one. This one says both two tasks called goodbye and farewell trigger once hello finishes, and they will simply echo it with some statement to stand it out. And you can visualize your suites with Cylc. The Cylc graph command. This one looks like that. You can also write your individual dependencies individually. You can put comments in there anyway. You can also trigger off, so this means goodbye triggers if hello succeeded, but you can trigger off task failure, start of execution, job submission, finish or fail, or custom output messages as well. I've already said that. An example of multi-line scripting. Right, this shows how you can make your job run somewhere else on a remote host using this batch system, PBS here, and some PBS directives. Simple as that. That's all you need. Cylc will create the job script and make it happen on that host. And then we'll track the progress of the task. Another thing we can illustrate here is, let's say we can run our job in a custom environment. So I'm defining an environment variable here called object, and this task goodbye echoes a statement involving that variable. And we'll do the same with this task farewell. Now there's some commonality here. They're both using the same environment variable. That's the maintenance risk in a large suite having duplicated configuration. So you can take those common elements and factor them out into a task family, which are called by or all. And these other two tasks simply inherit that. So anything at all, including job hosting configuration and so forth, can be inherited in this way. So you don't need to have any duplication in your suite. And this is just to note here that it's actually multiple inheritance, which is necessary if you want to avoid all duplication. You can use task families in the graph too, the dependency graph. So this says all of the members of this by all family trigger off hello. And you can trigger other tasks off families too. So this means if all of the members of by all have succeeded, we can trigger this task leave. Another way of writing the same thing there. I'll make it again. Just a quick illustration of what Ginger 2 code looks like, how it gets embedded in suite definition. Don't worry about the details at this stage. But this is setting a logical flag and cutting out a section of your suite depending on the value of it. And these can be taken as input from the external environment too, in various ways. That's another small suite that shows inheritance. I think I'll just skip over that to the graphical representation. So we've got a family called Ensemble, which has 3 members, model 0 through model 2. And in Cylc visualization and at runtime, families are collapsible and expandable and collapsible. So you can understand your suite in that way. You can also graph the inheritance structure of your suite to help understand. In fact, we have quite a number of command line tools to help you understand what's going on in a complex workflow. So this simply shows that those 3 tasks inherit all of their, or inherit configuration from this family, Ensemble. And everything inherits initially from a family called root by default. Another relatively new capability we have, something called parameterizepass. So here's a simple linear workflow, some pre-processing task, triggers a model run called sim, and there's post-processing and some final task. Let's say you want to replicate your model run across 5 different ensemble members. Here's how you can do that. Simply add this parameter n, or whatever you want to call it, and tell Cylc that it varies from 1 to 5. And Cylc will automatically replicate those tasks into an ensemble structure like that. Now you can do the same thing with multiple parameters if you like. So now we want to take another linear workflow and generate 3 different runs of an ensemble of 3 members for your simulation and post-processing. And that gets expanded automatically out into that sort of structure. So there's your 3 different runs in different colors of your 3-member ensemble simulation. Not the exciting bit. So we started the demo. I'll have to go fairly quickly. Sorry, but this is the last section before the demo, as I recall. So here's a simple workflow. Foo triggers bar and baz and a final task called cuts. I'm just making some space for what's to come here. So we're going to turn this simple one-off workflow into a cycling workflow like this. We have an initial cycle point of January 2010, and I'd say repeat this workflow from the initial cycle point on a monthly cycle. So this is essentially a simplification of an ISO 8601 date time recurrence expression. Run repeatedly from the initial cycle point on a monthly cycle. So that generates this kind of structure. Now, if you ran this in Cylc, all of these cycles could run simultaneously because there's no dependence between cycles, unless you put clock triggers on those tasks. Now, we can make something different happen at the first cycle like this. This says run once after the initial cycle point, a task called prep is what triggers the first foo. So that's a yellow star there. Then, anything I'm adding now is across an intercycle dependence. That's saying task foo in any particular monthly cycle depends on its previous instance 1 month ago, minus P1N. And that turns your workflow from this to your ongoing cycling structure, like you saw earlier. There's a bit of view of it. And you can tell Cylc to group the cycle points like that. Now finally, just to show you we can handle whatever kind of complexity you need in a workflow, I'm adding one more line at the bottom here. This says run twice at 2 months past the initial cycle point on a 1 month cycle. Add this task called boo, which depends on baz in the same cycle and cuts 2 months ago. So that's these red blobs. Now, you'd really need something like this, but if you do, we can do it. And just to finish up, 10 lines of configuration file, which is really rather simple to understand. All you need to understand is how to interpret these recurrence expressions. And they can be simplified from what I've shown. Like to do something just at the initial cycle point, you only need to write R1, say. Or if it's just a plain monthly cycle, you can just write P1N. And a graph structure which is intuitive to understand. The arrows represent dependencies. Simple as that, and you can generate quite a complex little workflow structure like that. And I'm not going to go through the other features because we don't have enough time, but I think it's worth saying that at this point, Cylc has been growing for almost 10 years, and we've got so much capability in there that I can't possibly cover it all in 1 hour. And you can look at the user guide or talk to Richard or myself later about other things. Right, so I'll attempt to do a demo now. Perhaps we should I pause for questions at this point before doing a demo? I've probably used up more time than I should. Does anybody have questions at this point?
Are you quite familiar with EC flow as a computer center? Can you know broadly how this differs from that?
I've talked to lots of people who use EC flow and its predecessor SNS. To my mind, EC flow is a huge monolithic system that is probably very good for operational systems, but it's much less useful for research and individual use, and it does not do this interleaved cycling like Cylc does. All right. Right, so I did a little demo. A couple of small workflows here. I'll start with one called Hello. Here it is. It's all like one of the examples of my presentation. Simple graph. Start triggers middle, triggers end, and they simply echo some stuff and sleep for a few seconds. The middle task sleeps for 60 seconds. And I can run it like this. I'm going to install the suite to a self-contained location and start up the suite theme for it and fire up the graphical interface. So here is that workflow running, and I can look at the graphical view there too. So I can right-click on any of these running tasks and do all sorts of things, such as view the job script, the standard out and standard error it's generating, what the status prerequisites are. You can view it in your own editor if you like. You can poll the task to see if it really is doing what Cylc thinks it's doing, even on another machine, or you can kill it, even on another machine. You can hold and release individual tasks. You can pause. I hit the pause button there. The entire workflow will pause, and you can see that here. The end task, which hadn't run yet, has gone to the held space, which is pink. Release it again, which means that any tasks that are ready to run will be submitted to run. I can get rid of the view there. So let's look at where the output from these jobs is going. It's all a nice self-contained location. Sort of run suite name log job. So there's the output file generated by the suite run for the three tasks: start, middle, and end. And each one has its own run directory. So that's cycle point, submit number. Nothing gets overwritten if you retry or re-trigger the job. Job standard out, job standard error, various other information, and the actual job script generated to run the job. And we also have ways of looking at job output without having to know exactly where it is. So, okay, middle dot one. So we we go. I'll look at the standard out for that task. There's the echoing hello. You can see here the communication back from the task job to the suite daemon. Started and succeeded messages of that in that case. Alright, so that's one simple demonstration. Now, there are many things you can do with this. You could, in fact, that'd be a good one for me to show you. I'll run this one again if it's not still running. It's not. So this time I'm going to kill the suite dead with the kill signal externally while the middle task is running. So this is to simulate a worst case scenario when an administrator kills your running workflow in the middle of operation, or the suite host goes down or whatever. So let's find it in process viewer. Cylc. Right. So this is a running workflow here. It's Python process, with a pool of sub-processes submitting jobs and so forth. I'm going to kill that with ckill, and you'll see that it's gone. Now I can simply restart that, and we'll take off from exactly the state it was in when it was last running, no matter what's happening at the time. And see how it says polled here? That indicates that on restart, the suite daemon actually went out to the system to determine that the task middle, which was orphaned when the suite was killed, was still running, and it updated the status accordingly. So it's very robust. There's pretty much nothing you can do that will stop you from resuming your workflow at any point, no matter what goes wrong. So feel free to interrupt with any questions you have at any point. Now, what else can I show you?
Any questions? Okay, there's a...
This is Terry McGinnis. I just had a few questions about the interactions that the system has with the various schedulers, and I see you can do even remotely, so like SSH in. And I saw that you defined the scheduler, and you only added the specifics that that job required. You had to kind of do that up front, and I guess you'd have to support different schedulers or use SSH and QStat. Maybe you can expand a little bit on that.
Yeah, so we have built-in support for all of the common schedulers, TBS, Slurm, load leveler. There's about, I don't know, 6 or 8 of them. And it can also be extended to new ones if we haven't got them covered fairly easily. So yes, if you're submitting to a job to a remote host and doing the job submission on that remote host, you need to have non-interactive SSH configured to do that. And for the communication back from the job host, you need, there's several ways of achieving that too, but the one we recommend is have a range of network ports open for HTTPS communication. But the job scheduler support is quite easy because we just submit jobs. It submits jobs just like a user does. So for PBS, it would simply generate a job script with all of the right directives in it and do a Q sub on the host where you want it to run. Okay?
So,
excuse me,
there's a question that has been put on the chat.
could you
Oh, yeah.
repeat that area?
Can you see the chat button there for the WebEx?
If you go to top of the
Sorry.
screen.
Just trying to find it.
You go to the top of the screen on your WebEx.
I see, yeah. Chat. Gotcha. Right. Make that bigger.
Could you everybody?
Yes.
Can you?
Sorry, you mentioned, can see it. You mentioned that it is not a good idea to run the Cylc server daemon directly in the HPC system. Why is that? Well, it's not the kind of process that HPC systems are meant to run. I mean, you have to be able to run potentially long-running Python process, and there might be a lot of network access required for that as well, to run the GUI clients and to interact with jobs and so forth. So, in my experience, HPC system administrators would typically rather you didn't do that on the HPC system. You typically have a dedicated VM for running Cylc suites that has access to the HPC and may even be within the HPC security trust zone for that purpose. But if you have the access, you can even run the suites on your own desktop box and submit jobs to the HPC. Okay. Number 2, suppose I'm running a long retrospective simulation. Do I need to keep the daemon running for a long period of time? Days. What happens if there's a machine failure and the daemon stops? Well, I think I've just demonstrated that. It's no problem at all if there's a machine failure and the daemon stops. You simply type Cylc restart and it will come back as it was. There is even an ultimate fallback option if you actually delete your suite state, which is held in a small database. You can do what's called a warm start, which starts again from a particular cycle. So we've never, in the history of using Cylc, had a disaster that couldn't be recovered from by one of those 2 methods. You can also generate checkpoints at any arbitrary point that you like, so that you can go back and start from again. So Cylc has throttle ability to control how many jobs are submitted simultaneously in case the dependencies are met for many jobs. Yes, it does. It has an internal queuing system, which is very easy to use. So you can define for particular groups of tasks, or for the whole suite, or both, a maximum number of tasks that can be active at once among that group. Okay? Now, we have a little time left. I could do a slightly better demo. Let's see. Okay, I'm going to run I should show you the best way of all dealing out. Okay, I'm in a suite called Demo 1 now.
Jordan, one more question in chat area.
Yep. Mm-hmm. Sure. Oh. How does Cylc handle file dependencies? That's a good question with quite an involved answer. We don't directly support file system events, if that's what you mean, because they are not very useful in a shared file system environment, which is typical in HPC sites. So you can easily make a workflow that depends in any way you like on the external world, such as the presence of files, by simply putting a task in your workflow which acts as a proxy and goes out and looks for whether that file is there, for instance. But we do also have a better method in the works that's currently up as a pull request on the Cylc repository in GitHub, where we can have a plug-in system for any arbitrary. It allows you to trigger a task of any arbitrary external event. You just have to supply a Python function which knows how to do that. And we'll have built-in support for certain things. So we will be able to handle file dependencies very nicely in that way. Okay?
Yes, thank you.
Right, so I have a slightly more complex suite here to show you a couple of things. I'm just going to run it. I won't look at the definition because we don't have enough time. So we're installing it, starting it up. Here it is. And let's look at the graph view as well. So, 2 tasks have failed here, deliberately. I made them fail. I will just I'll show you how you can manually trigger. So this task is called oops, it's not running because it's held back by that guy's failure. But I'll just manually trigger it. It's run now. So I want to show you something to it. This is going to fail too. Now I'm going to do something called edit run. I'll show you the kind of interactions you can do. So right click on that task that failed and choose edit run. That's going to generate a job script to run the task again and give it to me in my own editor, text editor. And I can see here that there's an error in the suite configuration. It's trying to run a task called hell.sh. Whoops. What the hell am I doing? Sorry. I just accidentally told my editor to open another file. So let's do that again. Edit run. So the job script, you can see, is actually quite short. It's only 40 lines of shell scripting with a bunch of environment variables and some communication and error tracking code that's hidden from you. And you can see just what you told the task to run here. And that's the error. It should be hello.sh. The script in the suite spin directory. And so I edit that, save it, exit, and Cylc's popping up a dialog saying, do you want to trigger the edited task? Yes. So that's going to run the task again. It should go. There it goes. And this time it'll succeed. Now I'll just leave that running and I'll just show you something else. So I can type row suite log here and it's going to fire up a nice web interface to the job log directory. This works really well even if you've got hundreds and hundreds of tasks which are cycling over a long time. You'll get quick, easy access to all of the job logs from that entire system and that entire run. So this is showing just that suite I was running, and here are all of the tasks, what happened to them, when they ran, where they ran, what their job IDs were. You can look at particular job scripts, job.out, job.error, standard error. So that's the task I just did an edit run on, and you can see that it failed the first time. Job exit status, and here's the error. So I could have used that before doing the edit run to find out what went wrong with it. But let's look at the, so now what I've done is clicked on the task name, which narrows down what I see to just task with that name. And you can see in the second run, 2 of 2, it succeeded. And we even have recorded in the job log directory at this file that shows what was changed in that edit run. So you have a complete record of everything that you did to the system at runtime. So there's the diff. I corrected hell.sh to hello.sh. So that's our job log viewer. So this is actually currently not part of Cylc. It's part of another open source system called Rose, but the viewer will be migrated to become part of the Cylc project itself in the coming year. So the hour is up. There's plenty more I can show you, including demonstrations if we had time. But any more questions, or would you like me to do more, or is time up?
I guess this is a pretty good point to stop now. We appreciate all the stuff that you provided here. Are there any questions in the room?